Hi guys, so we produced this script last week that helped us to plot different aerofoils. So this one here, let's move that arrow down a bit. This one here is the NACA 4415, which we can see because this the script has produced the NACA 4415. Let's go back up to the very top of this script and have a look. Take my annotation off. We had the equations for the camberline and the thickness, and these were then plotted out as different sub-functions of a global function called NACA 4, which we're then able to use here to plot different aerofoils. And what I've done is I've taken the NACA 4415, I've got the upper surface. Let's move this up a little bit. Okay, so I've got the upper surface. I've got my stylus isn't connected to the screen at all, so I've got to do this by sight. Got the lower surface, and then I've got the camber line between these two. So these are plotted just based off the number, which for this one, this was the NACA 4415, I think, was that right? Yeah, 4415. It's just basing those upon the number and using the function that we created to produce this upper and lower surface. And then if you'll recall, last week we've then got these data points which were taken from the UIUC website, and we've then plotted those over here to show that our functions work. So it would be nice if we could go the other way. So what we've got at the moment is we've got a function that if we have a number, we can then plot the aerofoil and we can then plot the points on top of it to check that we've done things properly. So we sort of validated this NACA 4, which was our function. It would be nice if we could start with these and then work out what are those three numbers, M, P, and TT. So if we could work out those numbers based upon the data, then we could take data, plot them, and then plot a NACA 4 series over on top of it. So we're going to do that today. Let's have a look at how we can do that. This is going to be hopefully a quick lecture, but there's probably going to be a lot of pausing and sort of stopping and working things out. I'm going to work on the NACA 4415. So this was based upon the UIUC. If you haven't got it, we can just go here and do a search for 4415, download this and put it in an area you have access to. So, okay, so I'm going to work in here. And I'm going to see if we can come up with some means of interpreting these data. So we're going to firstly look at these data points on their own and see what they look like. So I'm going to, well, we've already got them here. So what I'm going to do is just take, this is listed as being the Cessna drag polar here. It's not, this is the import the data. Let's work in this line here. I'm going to comment out this line. Let's just remind ourselves what everything's doing here. So NACA for 4415, what this one is doing is plotting the function that we wrote last week. Plots the upper and the lower surface. Then if we want to import the data and plot it on top of it, we can then do it this way around. So in fact, what I will do is I'm going to take these lines out, which is importing data, and I'm going to put them down here. So if I then make a new figure, plt.figure, I've then just got my data from this aerofoil taken out. So these data are in a slightly confusing format. So we don't know the order they go in just yet. We don't know how they work. We've just got some interesting data which is in an X and a Y format. So let's do print data. So I'm going to do cell. I want to toggle scrolling because I want to complete my output here. So this is my X. Let's move across. Sorry, this is my X column and this is my Y column. So we can see it starts at 1 at X and then goes all the way down to 0 and then goes up to 1 again. So it's starting at the trailing edge, going round and coming to the trailing edge again. So it's going all the way around the leading edge back to the trailing edge. And then we can see we've got positive values of Y at the beginning, so that must be the upper surface, and then negative values. So these values we think are going wrapping around the aerofoil, going from trailing edge all the way around back to the trailing edge again. This is actually what's called CLIG formats. Now that's just a generalized way that we describe aerofoils going from trailing edge all the way through to leading edge. We can confirm that that's the case if we weren't certain, because we can do, and this is a handy thing to be able to do, I can do let's do for I in length of data. Let's just see what this does. I'll do print I. Now this is just going to iterate over, it's because I want to do I in range, length of data. This is then going to give me I from all the way from 0 up to 96, which tells me there are 97 data points in this aerofoil. What I can do to confirm that my trailing edge along the upper surface back to the trailing edge again was correct is I can do plt.text, and every point I want to say take the x column, so we take the x coordinates and the y coordinates, and then just print the value of I there. So if I run this now, we can see that if I zoom in at the trailing edge, yep, I've got 1, 2, 3, 4, well, I've got 0, 1, 2, 3, 4. Coming back all the way back here, we've got the 96th point at the end. So we've confirmed the order of these data. This doesn't help us just yet. So let's think about what we actually want to do with these data. We've got, let's move this off. If we have an aerofoil, then that was a terrible aerofoil. Let's draw that again. Not much better. Let's try again a third time. That's slightly better. Okay, so this is our aerofoil. Remember, we've got the upper surface and we've got the lower surface. And what we've got in the middle is the camber line. So the camber line goes from 0 for our normalized aerofoil to 1. And we know it's a function, so it's yc is a function of the x location from 0 to 1, and then of those two other numbers, m and p. So it's the maximum camber and the location of the maximum camber. So this was the first digit in our NACA number, and this was the second digit in our NACA number. So when we were doing some plotting a couple of weeks ago, we had a CD, CL data to fit, and we said, okay, well, we know that CD is equal to CD naught plus K CL minus CL naught squared, and we did something kind of smart. We did an optimization where we worked out what these two numbers were based upon these data, and then we fitted through that. So we're going to do something smart as well. We're going to say, okay, well, if we can work out what the ordinates of our camber line are, then we can work out the parameters, because each of these is just going to be, let's say this is XC2 and YC2. There will be a number of these all the way along here. We can then work out very similarly what the M and the P that correspond to this curve are. And if we can do that, we've got the first two digits of our NACA aerofoil. So our first step is based upon those data we've got, can we reproduce what the camber line must look like? So let's get rid of these. We know that our camber line for this aerofoil looks something, haven't got a chance in hell of drawing this right on here. We basically need to know something like what the camber line looks like in this aerofoil. Just to reiterate, my tablet is not connected to this screen, so I've got no idea how to make these lines join up. So our first step is to take these data from this CLIG format, and we want to separate them into an upper and lower surface now. So let's work out where the leading edge is. The leading edge is going to be a point that has an x coordinate of 0. So let's just check we've actually got one of those. Let's get rid of these. Let's do print data. So there is a 0 point here, and we're going to, it's actually got a non-zero y point here, but we're going to include this point in both the upper and the lower surfaces, wherever that x is equal to 0. So we're then going to separate these curves out based around where the leading edge is. So what we're going to do is find where the leading edge is. We're going to take our data and I'm going to separate it into x and y. So I'll say my x is equal to data, and I want the first column, and the y is equal to, let's scroll up a bit, y is equal to the second column of my data. And then I want to find out where the x value is equal to 0. So I'm going to say the leading edge is where x is equal to 0. Now I know this won't be correct, but I want to show you what this is. So it'll print leading edge. So I've said the leading edge is equal to wherever x is equal to 0. Now this is going to give me a Boolean index, which is mostly false, but it has a single true value at the leading edge. So I'm then going to, rather than having a Boolean index, I'd like to know the number where that occurs. So I'll say np where. Let's see what this gives me now. This gives me a tuple, because I can see the brackets around here, and then it's got an array in here. So actually I only want the number 48, so I need to tell it to take the first item out of this tuple, and then I want the only item in that array. So I need to take here, I need to do, that's getting the first item out of the tuple. So this then tells me, okay, it's equal to an array of 48. And I then just want the number 48. So I'm going to tell it to take this out of it. Okay, so I've now got 48. And let's print this out to screen. Let's say f, the leading edge is at index in these data. Leading edge is index 48 in these data. So that's done what we wanted it to do. Now we're going to work out where the upper and the lower surface are based upon these. So let's so we know that the ceiling format goes from the trailing edge all the way through and round the leading edge to the trailing edge again. So I'm going to make a new array. I'll say my x upper is equal to my x starting at 0, so I can do a colon all the way to the leading edge. And because in Python, when we do this sort of slice notation, that says go to the leading edge but don't include it, I'm going to have a +1 there as well. Okay, and I want to do the same with my x. I want to get the same for the y coordinates out of this now as well. Let's do y of my upper surface is equal to y. Let's put spaces in here to make that clearer to read. I'll do print xu, print yu. Okay, so I've now got my x and my y of my upper and lower surface. Now, we could confirm these by plotting them again on the graph if we wanted to. Let's just do plt.plots xu, yu, and I'm going to put orange, or red, sorry, red circles. There we go. So we've got the upper surface out now. Now it's still going from the trailing edge to the leading edge. So the way to change this is to do np.flip around both of these. This is just going to change it, and if you've got an array going from 1 to 10, you'll get an array going from 10 to 1. So now let's do print xu. Let's just do it before and after. Okay, so before it was flipped, it started at leading edge, started at the trailing edge, went to the leading edge, and I've just changed it to go from the leading edge to the trailing edge. Okay, so let's do the same now with the lower surface. The lower surface is already going correctly from the leading edge to the trailing edge. So I can do XL is equal to MP, no, so it's going to be equal to X, and I want to start at the leading edge point and go to the end. And then Y of my lower surface is equal to X, so the Y, start at the leading edge point and go all the way to the end. And again, it's handy to check that we've got these correct, so I'll do plots, I'll do plt.plots, XL, YL, let's make green squares. And we can see we've correctly got the data for both of those. Okay, so we've got the leading edge and we've got the upper and the lower surface correctly out of here now. So, can we get the camber line based upon these? Well, let's have a look. So we know that the camber line is going to be the mean of all of these. So if we have the upper and the lower surfaces, let's just plot the upper surface on in the red circles again. So on X upper and Y upper. I could just work out the difference between each of these and get the mean at each location. Now I know this isn't going to work, but we're going to try and do it anyway. So let's see, let's say X of my camber line. So I'll say X of my camber line is equal to X of my upper surface. And Y of my camber line is equal to the mean of Y upper plus Y lower. Oh, it does like it. I'm allowed to do that in these. Let's try and plot these on. Okay, so it's allowing me to do this for this one. This won't always work. This method won't always work if you don't have the same size of each of these arrays. Now let's just do a quick check that these both have the same X location. And what I mean by this is that everywhere on this plot we're assuming that we've got the same X value in the same item of each array. So if as I go along, all I need to do is just do the mean of each item and it's going to give me the same location. So I now just want to check, have I got the same X in both of these? Let's just do a quick check. Print XC, let's do print X upper, print X lower. They look the same. Let's just do a subtraction of them. So I'll do print X lower, X upper minus X lower. Okay, so I've got the same points on both the upper and lower surface here, so that's actually helped me out a lot. If I didn't have those, then I would need to interpolate at each point. So let's just talk about what we'd need to do, because I know that some of the data you get off of the UIUC data point doesn't have the same number of data points in the upper and lower surface. Now let's just tell you what I mean by that. So if I've got data defining my upper surface, and I've got data defining, say, my lower surface, if these aren't necessarily at the same X location, so these are my X locations for the lower surface, and these are my X locations for the upper surface, it's not correct to say that then I know my middle point here is the mean of this one, and this one. Okay, so you have to be careful. So what we actually would need to do with this is say, well, let's work out where the points would be corresponding to opposite locations. Okay, so I could, the way that I would need to do this is to work out along this curve here, what is the value of the lower surface wherever I've got a point on the upper surface. And we've sort of done a bit of interpolation before. Let's just talk through how we can do this. So I'm going to make the camber line and let's bring the notes back up on screen. I'm going to do this interpolation method because it's important to know how to do this, but I think for some of the aerofoils that you guys might find, this method will end up throwing an error. So we'll say make the camber line, we'll say the x of the camber line is equal to the x of the upper surface. So we want every point on the camber line to be defined by wherever the upper surface has a point. So I'm then going to say make an interpolant for the lower surface. So I'll do from scipy.interpolate import interp1d. And then I'll say my function that defines my y location of my lower surface is equal to interp1d x lower, y lower, and I want to make a cubic interpolation. Cubic's normally a good fit with any sort of continuous curve like this. I've got a bunch of figures open at the moment, so because I'm running this one a lot, let's just do plt.close. That warning was telling me I had a bunch of figures open, so if you put close all at the top like I just done, it will stop that warning from coming up. So this now is then an object that if I give it some x data, it will give me out the corresponding y data. So in here, whereas previously I had yl, and I want to say f, yl, and the locations where I want to get the data are at xc. So if I run this, it still gives me all the same information, it still gives me this, but I've just made sure that this logic will work if I have an aerofoil with a dissimilar number of points on the upper and the lower surface. Okay, so this was, we sort of only added in an extra line and then we just changed a little bit in this line here to make that work. Okay, so now we've got the camber line. Now, using the equation for our camber line, now it's important to make sure you're using the version of the notebook I've shared for this lecture, because there was a bunch of errors in the last one and this one's completely right. So if I take that function for the camber line, let's just put this back down here. Okay, we don't need to actually double it again because it's already been defined earlier in the code. But if we can remember, we fit things using functions before. We did this when we were fitting to curves. We tried to get the drag bucket out with those data. We could then, using the optimization toolbox, work out what the parameters m and p have to be such that we can go through this curve here. So let's say so we're going to determine the curve parameters that go through that curve, which is just defined by those blue crosses. We're going to determine what the m and the p are that come out of that. So we'll do from scipy.optimize import curve fits. Now we'll use this a lot, or you should be using it a lot as we go through sort of your academic careers. So I'll say m, this is exactly the same syntax we followed before, so m and p, and then are going to be the first two things that come out, and then I'm going to get a bunch of parameters that I don't care about, so I set those to be ignored with an underscore. I want to use the curve fits, and the function that I'm trying to fit is camberline, and the data that I'm feeding are xc, yc. Let's do print m times 100, print p times 10. Okay, so I've got 4 and 3.8, close enough to 4 for our purposes, okay? It throws a warning here because it says divide by 0 encountered in double scalars. So this line here I can see is from our camberline function. It's from in here, and when it's going through, it's trying out different values of m and p in here, and as it goes through, it's saying at some point I've got a value, either it's put p is equal to 1, so it's got a 0. Yeah, it's attempted p is equal to 1 in here at some point, so it's tried to do a divide by 0. So it's a warning, it's not an error. In this case, it just says I've managed to finish, but there was an issue I had when I was trying to optimize this function. So this gives me 4 and, to no decimal places, these are 4 and 4 as integers, which for this aerofoil is correct, NACA 4415. So that's got my first 2 parameters sorted. So we can now just get the last parameter for this aerofoil, which is the thickness. So the thickness of these NACA series is based about the maximum thickness of all of them is based at the 30% chord. That's just a fact you guys can know. Let's just print our X upper a second and see if there's data at the, yeah, there's values just before and just after 30%. I mean, this is really close to the 30% chord, but we're going to interpolate this. So we have already got an interpolant that defines the lower surface. So what we'd like to know is we'd like to know what is the actual value in between those 2 data points at 30% chord. So I'm going to make a similar interpolant for the upper surface now. So Fy upper is equal to y x upper, y upper. And I'm going to say make an interpolant for the upper and lower surfaces. So I then need to use those, and I'm going to work out what the thickness is at the 30% line. And then if I get the difference between them, that will give me the thickness. So T is going to be equal to whatever the value is of my function, which is the upper surface at 0.3 chord, minus F YL 0.3. It's going to put a 0 here rather than a minus. Okay, thickness it gets 0.15, 15%. So we've got NACA 4415 here. So let's just put these data out. Let's, rather than printing them like this, let's do so we'll say aerofoil number. Remember, it's a 4-digit term, and it should be a string. So let's say it's going to be, the first digit is the M, expressed as a single digit, expressed as a percentage. So it's M times 100, and I want to put it with no decimal places. Second digit is going to be P in tenths of chord, so I need to multiply it by 10 with no decimal places. And then I want the thickness defined as a percentage, again with no decimal places. So let's do prints. I think that the data in file, now the input file was given by the file name up here, so I can say file name is a NACA aerofoil number. I think that the data in file 4415 is a NACA 4415. So it hasn't taken any information about that file name. It's taken the data and it's worked out what sort of aerofoil it must be. So what we can now do is let's go through and just get rid of all of these. Let's just comment these lines out where we plotted. Let's check these are all gone. No, I've still got one set of data there. Let's get rid of that one. It's opening up a figure, we don't want it to do that either. Let's comment that one out. What we can now do is go down here and I can say plots the aerofoil from the function before. So I can do NACA 4 aerofoil number, which is going to use the function we wrote last week to plot this aerofoil, and I can then actually just take this line here, plot this one on. There we go. So let's play around with this a little bit more as well. Actually, let's just plot on the camber line as well. Why not? So just to show that we've got some data here as well. Show that the camber line matches the camber line based upon the function that we wrote last week. So we've taken a different approach now. So rather than taking the number and typing it in here, we've been able to take the data, work out what the NACA aerofoil must be. So it says here, I think the data in this file is a NACA 4415. It then plots the aerofoil and then plots those data overlaid on top of it, which is pretty damn smart. Let's just try this with another aerofoil. I know that in my data repository, I've got a NACA 2421 as well. Let's just see if this works. Run this. I think the data in file NACA 2421 is a NACA 2421, and then tells me stuff about it, and it then plots it. That's pretty smart, guys. That's a pretty useful function. Let's just go back up to our plotting function up here, and let's do some things that help us actually show what we're plotting here. So I'm going to give labels to these as well. So let's do label equals upper surface. Label equals, let's say, and these are based from the NACA 4 function. And do I plot the camber line here? I do as well. I'll say in fact, let's make this an F string. We're going to put in the number as well here. So we'll say NACA 4. No, I'm not. I'm going to say number here. So with an F string, that's got to be within those curly braces in there. So let's do the same to these actually. Let's make these both F strings. And rather than NACA 4, I'm going to put the number parameter. So if I run this, that's just run that to redefine that function. I can then go down here, and when I'm running this, just at the very end, I can do plt.legend. Doesn't like that. Camber line, got an unexpected keyword argument label. Oh, that's why, because some of you might have spotted what I did wrong there. I've gone through and I have added a label to this line up here, which is not what I wanted. I added a label to this camber line. I should have put this label in down here. Let's run that. What isn't it like? Not like here. Okay, so label says when I try and trace errors, guys, go down to the bottom. It normally tells you what the error is. Line 2G object has no property labrula. Okay, so that means I've misspelt label somewhere up here. It's right here. Fat fingers fall again. Well, not so much fat fingers, broken fingers. I'm still struggling with my left hand quite a bit. There we go. Okay. So the legend is overlaying it at the moment. Let's do some messing around with the legend. Let's just save this in here. Let's do label equals data file name. And we'll do plt.title, data from file name, and there we go. So we're going to give it a title. It says data from file name and estimated NACA aerofoil number, and then we're going to do some other things. So I'm going to get rid of the axis. I'll do plt, and I want to get the axis, get current axis, and I'm then going to set it to axis off. Okay, data from that data file on the estimated fit. Now this legend is over the top of my plot at the moment, so there's a bit of funky syntax we have to write to get rid of this. I'll do plt dot get the current axis because the legend belongs to that axis. and I'm going to tell it, say, legend. You tell it that the bounding box, bbox underscore to anchor, we want it to just exist over to the right. So we'll say I want it to be at 1 point, so equals, and then a tuple, 1.1, let's say 1.05. These numbers normally work for me. Nope, that doesn't work. Why did that not work? Oh, it's because I moved the legend before I moved it. Now, why is that small? Let's see if I can change this to, say, 0.5. There we go. 0.5, and let's make this to 1.1. So these are the x and the y coordinates where I want my legend to be. There we go. So what we've got now is we've got our aerofoil. We started out by importing some data, working out what the aerofoil around it must be, and then plotting the data based upon our functions that we had before, the camber line, the upper surface and the lower surface, based just upon that number and the function we wrote last week. And then we've then plotted the data back on top of that. So let's try this with one more aerofoil that we've got. I've got a NACA 1412. Let's try that. So I'm going to go here, 1412. There we go. Looks pretty good to me. Okay, so we've done something really quite smart there, guys. This is really useful to do. It might sound like a contrived example to you guys. I promise you this isn't. So I do a lot of work on sort of propeller aerofoils and coming up with a parametric fit for different profiles through, say, sections that are maybe slightly off design, but actually we know must be some form of pre-existing aerofoil shape, and just working out what those parameters are, that's really powerful. And again, this is one of those lessons today that I think maybe you might not have fully grasped this week. Some of you will have, and that's great. Some of you might be thinking, hey, what the fuck have we done? What have we actually been looking at today? And that's fine. As long as you've gone through and you've got this saved and you've got the examples with the comments about it, then when it comes time to do this sort of work in 1, 2, 3 years' time in your academic studies, you'll have this to look back at and you think, ah, man, I'm glad I went through that. Yeah, Professor Smith showed me this and I've got an example of this based in my notes. So guys, went through this kind of quickly today. It's because I've recorded this twice through with 2 audio failures and I had no energy left to record it with all my zeal and doing it slowly and explaining everything. So if there's any questions, please drop a message on Slack and I look forward to hearing from you guys on Wednesday. Take care.